Okay, we're on question 9. We want to determine whether Rolle's theorem can be applied. And if so, we want to find some critical numbers that lie between those endpoints. Rolle's theorem says really this: if f of one endpoint A is equal to f of the other endpoint B, and we have a closed interval, and it's differentiable, then there must lie at least one value C such that f of C equals 0. In other words, there's going to be a critical number within that closed interval if the function values at the endpoints are the same. Okay? We're going to go ahead and expand this into a trinomial of the third degree. And so we're going to have f of x equal, and if we multiplied those out, we would get x cubed. I said a trinomial, it's going to have 4 terms, but it's going to be a third degree polynomial. So x to the third, and then minus 6x plus 11x minus 6. And we can multiply those out, but we're going to just save the time and do that. So to verify that Rolle's theorem applies, we need to find the function value at this endpoint 1 and the function value at that endpoint 3. So we're going to say f of 1 equal, and then f of 3 equal. So we'll plug a 1 in there, so we're going to have 1 cubed minus 6 times 1.
This is being squared.
Square right here. Well, I keep not writing stuff down there. That's a square right there. Thank you, sir. So we've got 1 cubed minus 6 times 1 square plus 11 times 1 minus 6. And then if we plug in the 3, we would have 3 cubed minus 6 times 3 squared plus 11 times 3 minus 6. On the first one, we would have a 1 minus 6 is a negative 5. A negative 5 plus 11 is a positive 6. And a positive 6 minus 6 is 0. On the second one, we would have a 9. And a 9 minus 54 is a
27.
A 27. We have a 27.
Mr. Edwards
We
comes
have
out
a
and plays
negative
Ricky
54.
Edwards.
We have a positive 33 and a negative 6. So that's going to give us a 60. A 60 minus 54 is a positive 6. A positive 6 minus 6 is 0. So the function value at each endpoint is 0. We could have known that. Looking at that and that, those would have been zeros or x-intercepts, so we could have kind of fudged it, stuck it in right there and said, oh. Okay. That verifies to us that the endpoints have the same function value. This is a polynomial function, if we look at it here. Therefore, we realize that it is going to be continuous over that interval, and it will be differentiable because it's a polynomial. So we now want to find that C value or C values that would create a tangent or a derivative of 0 or a tangent line with a slope of 0, which would create a critical number, possibly a maximum, minimum, or later on maybe even a point of inflection. So we're going to take the derivative. We're going to have f prime of x is equal to 3x squared minus 12x plus 11. And then we need to do what? Set it equal to 0. We want to find where the derivative is 0. So we set it equal to 0, so we're going to have 3x squared minus 12x plus 11 equals 0. We might think, well, we could use the AC method, but if it has radical factors, it's not going to work, so we just as well go ahead and use the quadratic formula. It looks like it might have some challenging possibilities. 3 times 11 is 33, and we'd be finding factors of 33, which is 3 and 11, trying to get a 12 out of that. You add them, you get 14. You subtract them, you get 8. You're not going to make it with the AC method. You can do some little quick stuff in your head. And so we're going to use the quadratic formula. We're going to have x is equal to the opposite of b. My b was a negative 12, the opposite of which is a positive 12, plus or minus the square root of my b value, which is negative 12 quantity square, minus 4 times my a value of 3 times my c value of 11, all over 2 times my a value of 3. Now I want to write that on the board in case there's somebody that doesn't remember. We hope that you do. But anyway, it's the opposite of b plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. So we're plugging the a, b, c of the quadratic into that quadratic formula. Now, we're going to do the exponent, do this multiplication, and do that multiplication. So we'll have x is equal to 12 plus or minus the square root of negative 12 quantity squared is 144. 4 times 11 is 44 times 3 is 132, is that correct? When you multiply with an odd number of negatives, the answer is negative. 44, be 112, the 12 and a 12 scooted over will be a 1, 3, and a 2, all over 6. Now, we can finish under that radical. So we're going to have x is equal to 12 plus or minus the square root of 144 minus 32 is 12, all over 6. Now, the square root of 12 does not come out even. So remember, we take the 12 divided by 2 is 6, divided by 2 is 3. We have a pair of 2's, remember that. So we're going to have x is equal to 12 plus or minus. Pop out that 2, square root 3 over 6. Remember, simplifying those radicals from somewhere back in our algebra. Now, because these three numbers, every term in the numerator and denominator is divisible by 2, we can simplify that by a factor of 2. I'm going to clean out this side of the board over here. And so that would simplify to x is equal to 12, we're going to divide by 2, 6 plus or minus the square root of 3 over 3. Okay? 6 plus or minus the square root of 3 over 3. These are the values of c at which the derivative is 0. And you could separate those into the plus and then the minus, or we can leave it like that. So there's our two answers. 6 plus square root 3 over 3 and 6 minus square root 3 over 3. Any questions on number 9? Okay. All right, number 10. Number 10, we want to determine whether Rolle's theorem applies. And if it does, then we want to find all values of c so that the derivative is equal to 0. Okay? So we first could find the function value. And so we might want to look at this and say, okay, is this factorable? I haven't even thought about that. But if we had a negative 3 with that factors, is there something we could multiply to get negative 3 and add to get a negative 2? We could factor into an x minus 3 times an x plus 1. We were hoping maybe that would cancel down here, but it didn't. So I thought, well, it's worth looking to see if there's a cancellation opportunity. And there's not, so this one's not going to get much better. But by doing that, you can notice that the function value, the numerator there would be 0, and 0 divided by anything is 0. So we can easily see by that f of -1 is 0. And if you plug that in there, you would see that that would create a 0 in the numerator. And so we can also see that f of 3 is 0. Now, we could have plugged them into the original function, but we understand if the numerator is 0, then the answer is 0. And by factoring, that made that kind of visible for us. Okay. We did not get a cancellation opportunity, though, to make our derivative process any better. So we'll just kind of get to deal with that. Okay. All right. So we want to find the derivative, and we'll do it from the original way that it looks. And so that is the derivative of a quotient. Now, how do you find the derivative of a quotient? You take the denominator
Times the derivative of the numerator.
times, so we put in parentheses, the derivative of the numerator,
Minus
so it's times that, right? Which would give us,
2x minus 2.
so denominator times derivative of numerator, and then minus,
Numerator.
I'm going to have to move that, minus the numerator,
X squared.
x squared, minus 2x minus 3 times
The derivative of
the derivative of the denominator, which is 1,
all over.
good, all over the denominator squared. Good. Excellent. Denominator times derivative of numerator minus numerator times derivative of denominator all over denominator squared. So we're going to clean this up a little bit. F prime of x is equal to. Now, if we multiply this out, we would have 2x squared minus 2x plus 4x minus 4. If we distribute that negative, that's not going to have an effect. The positive one's not going to have an effect, but distributing the negative one gives us a minus x squared and a plus 2x and a plus 3 all over that x plus 2 quantity squared. We'll combine the like terms that are in the numerator there, and we'll have f prime of x is equal to, we've got a 2x squared and a negative x squared, which gives me an x squared. I've got a minus 2x and a plus 4x, which gives me a 2x. And then another 2x gives me a 4x. And then I've got a negative 4 and a positive 3, which gives me a minus 1. All over x plus 2 quantity squared. I see no factoring opportunity for the numerator. If we could get an x plus 2 factor out of the numerator, it would cancel with one of the x plus 2's in the denominator. But that's not looking like a possibility. And so that looks like the best that we can do. So we need to think about where would that be equal to 0. For that to be 0, because we want the function at the place where the function value is 0 at, right? For it to be 0, what needs to be 0? The numerator or the denominator? Numerator. If the numerator is equal to 0, then the function value is 0. If the denominator is equal to 0, then the function value is undefined. Now the direction said f prime of c equal 0, so we're not concerned about the undefined. A negative 2 here, would that create an undefined? Yeah, because you get 0 squared, and then division by 0 is undefined. And so it would create an undefined situation, which is a critical number, right? But it didn't ask us for that, it only asked us for the 0. So to solve this quadratic, it's not going to factor, so we're going to have to use the quadratic formula again. So we're going to have x is equal to the opposite of b, negative 4, plus or minus the square root of my b value of 4 squared, minus 4 times my a value that understood 1, times my C value of -1, all over 2 times that understood A value of 1. And so we're going to have x is equal to -4 plus or minus the square root of 4 squared is 16. -4 times 1 times -1. You've got an even number of negatives, so the answer is a positive or plus 4. All over the 2 times 1 is 2. We're going to add underneath that radical, and so we're going to have x is equal to -4 plus or minus the square root of 20 over 2. The 20 is not a perfect square, so we're going to break it down. Doing the prime factorization, divided by 2 is 10, divided by 2 is 5. We have a pair of 2's, so out pops a 2. And so we're going to have x is equal to -4 plus or minus 2 square roots of 5 over 2. All 4 terms that we see are divisible by 2. So we'll divide each by 2, and we'll have x is equal to -2 plus or minus square root of 5 over 1. So there's our 2 solutions. So our solutions are -2 plus square root 5 or -2 minus square root 5. We've got to check something out. And we really did on the last one, we should have checked them out. We should have took that 6 plus square root 3 over 3 and see is it within the interval of 1 to 3, right? It is supposed to be in a closed interval on number 9. It would have been. And if you had tried the second value, 6 minus square root 3 over 3, it would have been in the interval of 1 to 3, so it's a keeper. Well, we got to check these out. If we do -2 plus square root 5, we would say, is that in the interval, the x equals -2 plus square root 5? We're going to get some answer that needs to be between -1 and 3. And it would be between -1 and 3. 1, 2, 3 something. If we did the x equal -2 minus square root 5, you can see obviously that's going to be less than -1. That is not within the interval. So we can't circle that because only the plus route is a solution. So be sure that the solution that we choose is within the given interval. We have to remember that. We didn't check those on number 9. We should go back and check those. Is that value in between the endpoints of the interval? Any questions on 9 and 10? Okay. All right, number 11. Number 11 says f of x is equal to sine x. We want to see if Rolle's theorem applies. First of all, for Rolle's theorem to apply, what must be true? F of A must be equal to F of B. So what is the sine of 0 degrees?
0.
And what is the sine of 2 pi degrees?
0.
So we know that the function value is the same. We could graphically think about this, right? This is a sine wave. It's going +1 and -1. It's going to get halfway through its period in pi. Oops, I should move that over. It's going to make a full period in 2 pi. It starts at 0, it's going to go to 1, come back down to 0, go to -1, and come back up. Okay? Now, we have to ask, is it continuous within that interval? Well, yeah, we never pulled a pencil up to do that. Is it differentiable at every point on there? Yes. There's not a place where there's an asymptote. So it's continuous, differentiable, and the derivative of the endpoints is the same, therefore Rolle's theorem applies. Okay, so Rolle's theorem does apply, so now we want to find the derivative and then set it equal to 0. So we're going to find the derivative. So the derivative of sine x is cosine x. And we want to set that equal to 0, so we say cosine of x is equal to 0. And so our question is this: what has a cosine value of 0? Well, the first time is pi over 2. And then again at 3 pi over 2. And then again and again and again and again and again and again and again, but
It has to.
it has to stay within the interval of 0 to 2 pi. So the interval of 0 to 2 pi is going to happen here and here, and if we tried to go back, we would have gone pi, 2 pi. We can't go back up there the next time because we've gone out of our interval. So our two choices then are x equal pi over 2 and x equal 3 pi over 2. Any questions on that? All right. Well, that's lesson 3.1 and 3.2. Hope you do well.